Hello everybody. In this class, we shall look at counter design using asynchronous reset and preset. We have been seeing in earlier classes that some of the ICs, counter ICs having internal AND gate, logic AND gate, and there are two inputs to it, and we told that from the truth table they can be used for resetting purposes. And in IC 7490A we had seen that there can be a preset of 1001 as well. Again there is an internal AND gate. So, we actually were surprised why such thing is there, why that internal AND gate is there, why not only one pin. So, it will be clear from today's discussion that how asynchronous reset can be used to get different kind of modulo number, and those internal inputs and the internal AND gate can come useful in this particular context. So, that will eliminate the requirement of additional external AND gate and placing another IC, taking more space, wiring and other things. So, those can be prevented. So, let us see IC 7490A. Okay, with that we are looking at. So, we are already familiar with this circuit, this IC. It is a mod 10 counter, and if we connect it appropriately, that means mod 2 followed by mod 5, then it acts like a BCD counter. So, BCD counter means it goes from 00, 00, 00, 01 up to 1001, that is 9, decimal equivalent 9, then again it goes to 0000. So, that is what we know. Okay, we have seen in the previous class, right. So, the IC 7490A, this particular BCD counter has been connected in this manner. Okay. So, clock is fed to mod 2 counter, and QA output is fed to as clock to mod 5 counter, okay, and restart the ABCD are the QA, QB, QC, QD, these are the outputs. Okay. So, the count in that particular counter with clocking as given here will go on as I have mentioned here 0000 to 1001 and then again 0000. Okay. This we are already familiar with. Now, if you are connecting QB and QC output, 8 and 9 output, one of them is going to 2, another is going to 3, right. So, if you do that, what will happen? So, these are R01 and R02. Okay. So, these asynchronous reset input, internally there is an AND gate. Okay. So, when both of them are high, then what happens? These particular outputs are asynchronously reset. This counter is asynchronously reset. That means, immediately after a short time of that propagation delay of the internal AND gate, all the values get 0. This QA, QB, QC, QD, all of them acquire the value 0. Okay. So, the counter is having a very short duration, some number associated with this, okay, and then it goes to 0, 0, 0, 0. Okay. So, with the count happening 0, 0, 0, 0, 0, 0, 0, 1 that way, what is the first instance when these two become 1, 1? So, that it goes to 0, 0, 0, 0, again it goes on counting similarly, I mean the way the clock gets triggered. So, if we follow the counting sequence, we can see that 0, 0, 0, 0, then 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. You note that QC and QB are fed. Okay. So, this is your QC and this is your QB. After that 0, 1, 0, 0, 0, 1, 0, 1, and then comes 0, 1, 1, 0. So, this is the first time in this counting sequence, as you see that QC and QB, both of them are becoming 1. Okay. And when both of them are becoming 1, immediately, that means after that short propagation delay, which is much less than the time period of the clock. Okay. So, what is happening? It is immediately going to 0, 0, 0, 0. So, in that particular clock cycle, you are effectively having, for larger duration, effectively you are having 0 0 0 0. So, that means you are back to this particular number, this particular state. Okay. Is it fine? So, what are the then unique states for which the clock period, during the clock period the counter holds a specific value. So, these are the 0 0 0 0 2 0 1 0 1. Okay. After that it again goes to 0 0 0 for very small duration, staying at 0 1 1 0. Okay. So, effectively you are having 0 1 2 3 4 5 and again back to 0, right. So, 6 unique states. Okay. So, this is called, this is behaving like a mod 6 counter, and if you had required to do this by external connection, then we would have required a 2 input AND gate, okay, and then that output would have been fed to one of the input. So, that additional circuitry wiring and putting another IC 7408, powering it and all those things are not required, and that need is eliminated. Okay. Now, having noted this, that 0 0 0 0 2 0 1 0 1 and the value wherever it goes, then that and 0 0 stays together in this particular mode. Okay. So, if QD and QA, right, this is QD and this is QA, right, if they are sent here instead of QC and QB, right, QC and QA are sent, now we are sending QD and QA to this asynchronous reset. What will happen then? Okay. So, it will go from 0 0 0 0 to first time whenever it goes to both of them, QD and QA becomes 1, that is 1 0 0 0 1, immediately it gets reset. So, that means for a very short duration it will be there, and then 0 0 0 0 will be there. Okay. Right. So, effectively you are having 0 to 8, 1 0 0 0, and in this particular clock cycle 0 0 0 0 is again appearing, okay, because of this asynchronous reset. So, effectively you are having 0 to 8, that means 9 unique states. So, it behaves like a mod 9 counter. Okay. If you want a mod 8 counter, so what is the first occasion when this is how this is the count. So, 0 0 0 0. So, 1 0 0 0, this is the time when you want to reset it. Okay. So, before that you had 0 1 1 1, right, you want 1 0 0 0 and 0 0 0 0 at one particular clock cycle. This is the one with which you want to reset it. Okay. So, 1 has not come before, 1 is coming for the first time, right. So, 1 QD you can feed to, just take a wire and connect to both of them, that is fine, internally it is getting ANDed, both the input are 1. Okay. So, that way you can get mod 6, that way you can get mod 8, that way you can get mod 9, right. But how, if you want to get a mod 7, right, then the first time it is happening, it is 0 1 1 1. Okay. Now, with 2 inputs, okay, it is not possible, because if you give just these 2, then it is mod 6. Okay. First time it will occur when 0 1 1 0, and if you want to give these 2 inputs, right, that will also occur when it is 3, and if you want to give QC and QA, that occurs when it is 5, isn't it. So, you need all the 3 inputs this QC, QB, QA, for which you will be needing an external gate, okay, in this particular arrangement. Is it fine? Okay. But otherwise, you can see that for the other cases, we are having this other modulo number obtained by just connecting wires in this manner. Now, we shall look at something which is where the use of fixed preset, which is there with 7490A, that we shall exploit, okay, for this modulo number design. So, here we had seen that when R91 and R92, R9 means it is setting a value 9, 1001. Okay. So, when this 6 and 7 earlier we have kept at ground because this is the one that we are using it, right. So, if we keep 2 and 3 ground and 6 and this 6 and 7 where R9 1 and R9 2 are there. Okay. So, if both of them are high, then what happens? 1001, this is 1001 gets loaded, isn't it? 1001 gets loaded. Instead of 0000, it is now will be having a value 1001. So, we take note of this from the truth table and then we go forward. So, what has been done here? What you can see is that it is again a BCD counter, right. 2 and 3 now is kept at ground. So, there is no resetting happening, asynchronous resetting happening. Asynchronous preset can occur if right condition appears, otherwise it will be normal count as it was in the previous case. So, if you are having in the previous case 0 1 1 0, the same thing, right. So, 0 1 1 0 means QB and QC. So, first time it is occurring in the counting sequence, say if you have started from 0 0 0 0, if you have started from there, it goes on and then when first time it is occurring here and then it is getting what 6 and 7. So, R9 1 and R9 2 internally it is AND gate is there. So, both of them are high. So, 1 0 0 1 will be appearing, very short duration it will be there, after that 1 0 0 1 will be there. So, primarily this particular state is 1 0 0 1 having the value counted value 1 0 0 1, okay, except for that small propagation delay associated with the internal AND gate. Okay. So, this 1 0 0 1, right, when it gets loaded, after that what will happen? It is normal count, usual count. So, after 1 0 0 1, 0 0 0 0 will come, then 0 0 0 1 will come and that way it will continue. After again when it comes 0 1 1 0, it will get reset, again it will get preset, that fixed preset it will occur. So, the counting sequence, counting states, unique states are 1 0 0 1, 0 0 0 0 and then it goes on up to 0 1 0 1 and then again it goes back to 1 0 0 1. So, you have got now 6 unique states, 7 unique states, 1, 2, 3, 4, 5, 6 and 1 0 0 1 got added, right. So, 7 unit states. So, what is it? It is a mod 7 counter, right. So, mod 7 counter also you can get it, okay, without any additional gate and all, if you use the fixed preset part of it. Is it fine? Okay. And there can be other uses as well, right. Now, we look at another IC where some such preset is there, but that is variable preset. Here there was a fixed preset. So, here we have got variable preset, that means we can load numbers other than 1001. 1001 is possible, any other number, that we shall see how it works. Okay. So, this is IC 74193. Okay. So, IC 74193 interestingly has got various features. So, first of all, it is a synchronous 4-bit up down counter. So, it can count both in the up direction, that means 0 1 2 3 4, and also in the down direction, that means 15 14 13 2 etc. Okay. And for this you have got 2 clock input, right. So, when one of them is active, the other one should be inactive. So, if it is other one need to be held at logic high. Why? You can see there is a OR gate, then it is going to the input. So, if it is at high, then this output is low. So, then other input of the OR gate to which the other clock has been fed, okay. So, that clock will take over the output, okay, and accordingly the clocking will take place. Is it fine? So, that clock input, the one that is not used will be kept at high, right. And other thing that is important here, we know that this QB, QC, QD, QA, the uncomplemented outputs will take role when we are going for up counting, and complemented outputs they will be participating when we are going for down counting. Okay. So, basically the number of they need to be ANDed. So, and depending on count up or count down, whether ABC for here or A prime, B prime, C prime, that will be fed here, and similarly AB or a prime b prime, okay, a or a prime, that is the thing that will come here. So, these are the things that we already know from synchronous up counter, down counter design. So, those things are over here. Okay. See, the other thing important in this particular IC is that there is a load input, there is a clear input, that is reset. So, all of them get resets 0 0 0 0. So, there is a single input. Okay. So, there is no such facility available that two inputs are there and all, and you will see that it is not required because of this variable preset that is there. So, you can get different kind of modulo number easily. Okay. So, this is a single input clear, right, and then there is a load input. Okay. So, whenever it is activated asynchronously, whatever number is there D, C, B, A, that will come to QD, QC, QB and QA respectively, okay, without the need of the clock. So, immediately it will come after the this get delays and all. So, it will get transferred to the output. Okay. So, this is a parallelly getting loaded, okay, asynchronously getting preset. So, this is variable because DCBA value can be different, right. So, the idea is if you are basically putting a 1, then you are presetting it. If you are putting a 0, you are resetting it, is clearing it, the corresponding flip flop. So, similarly for other bits, right. So, other than this, you have got a carry output and borrow output here. So, whenever the number is increasing, say 0, 1, 2, 3, 4, going to say 15 in count up mode, then it has reached 15 and it is going to say 0 next cycle. Okay, next clock cycle. So, it has reached 15, the clock has gone low, that it is a positive edge triggered. Okay. So, you can see here is a inverter and here is a inverter. So, effectively it is a positive edge trigger, right. So, with two inverter from here, from this side, from the input side. Okay. So, whenever the counter clock input goes low in the second half of it, right, and the value is 15, then at that time the carry output will be active, okay, only for that small duration, as long as this clock input is remaining low, and borrow output will be happening in the other direction when it is getting the count is from 4, 3, 2, 1, 0. So, when it goes to 0, that means all of them are 0 and count down clock is at logic low in the second half of the clock cycle. At that time it will be active, okay. Otherwise they will not be active, okay. And this is the count up, count down, the sequence that we can see. Is it okay? So, we shall see its performance with timing diagram, that will make it more clear. Okay. So, this is the timing diagram I was talking about. So, you see the initially the counter may have some value QA, QB, QC, QD over here, right. So, whenever you are giving a clear, right. So, all of them are getting cleared, okay, asynchronously cleared, okay. So, you can see that all of them are cleared, right. So, after that clear input is taken away, is inactive, right. So, cleared is a, you can see is a active high, right. And then in A, B, C, D, right, these are the data that is input of it. So, at the input you are putting a value, D is 1, C is 1, B is 0 and A is 1, right. And whenever you give load which is active low, it make it low, what will happen? Earlier it was remaining cleared, okay. So, whenever you do that, this QD, QC, QB, QA, they take these values. So, now they become 1, 1, 0, 1, right. So, that is what has been shown here as 13 getting loaded, right. So, the clock in these cases when it was happening, clock was at logic high, okay. So, then the OR gate output was 0. So, basically there is no change, clock was, there is no clocking happening, right. Now, the clock countdown that is remaining at high. So, that means it is inactive, it is not playing any role in the clocking, and count out has started clocking. Okay. So, and when what you can see in the positive edges, this QE, QD, QC, QB, QA, the value start changing, right? I mean, get triggered. So, after 13 at the positive edge, what will happen? It will go to 14. After that, it will go to 15. After that, it will go to 0, 1, 2, and so on, 3. But what you are doing just to show that how countdown happens, to illustrate that. Okay. So, after that, you consider that count up has remained high. Okay. So, no more clocking. So, no more state change, it is remaining at 2, and countdown was also high. So, it is remaining at, there is no clock, even countdown clock also. So, it is remaining at that particular value. Okay. So, what you can see here 0, 0, 0, 1, 0, that is 2. Then what happens? Count up remains at high and countdown starts clocking. Okay. So, at its positive edge, what will happen? So, from 2 it will go to 1, then 0, then 15, then 14, then 13. So, that is how it works. So, I understand that with this illustration there is more clarity about how this clocking and counting takes place, and along with the parallel load and clear. Okay. The other thing is that you can see when it is at 15 and clock is at logic low. Okay. From the logic circuit also you can see that happening. So, the carry is remaining low, okay, for this half clock cycle duration, and similarly Bordeaux is for when it is 0 and for this half clock cycle duration. Is it fine? Okay. Now, let us see how it helps in getting different modulo number. Okay. So, we have seen this particular state transition diagram 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, again 0, 1, 2, this is the standard mod 16 counter, states are 0 to 15. Is it fine? Right. Now, we consider that we have put an external gate, okay. QA, QB, QC, QD, they are connected. So, it is a 4 input NAND gate, okay. And so, its output will be low when all of them are 1, because for NAND gate any input is low means output is high. So, all of them are 1, it becomes low. As soon as all of them are 1, it will become low. And this is sent to what? This is sent to your parallel load, that is asynchronous preset input, which is active low. Okay. Now, for different condition, different data input will be having different data now getting loaded whenever this parallel load occurs, okay, asynchronously within the same clock period, right, after the whatever this small propagation delay is there with the basic gate, right. So, if you have got your DCBA data input at that time is 1001, what will happen? Whenever this reaches 15, immediately in that clock cycle, the way we had discussed it for 7490, right, 9 gets loaded, because it is now variable preset. So, now it is 1001 like before, but we have now put external values 1, 0, 0, 1 separately. Earlier it was preset, you need to do it for 7490, 1001 was internally getting loaded, getting preset. Okay. So, it will go to 9. So, 9, 10, 11 it is in up count mode, right. It will, if you are putting it in up count mode. So, 9, 10, 11, 12, 13, 14, again as soon as it reaches 15 asynchronous reset. So, 15 and 9 are together in one clock cycle, right, and then again it will go on. So, you have got 9, 10, 11, 12, 13, 14 a mod 6 counter available with you, right. And had it been a down counter, if you had exchanged the role of the clock, one of the clock is now countdown clock is active and count up clock is held at logic high, then what would have happened? Okay. So, after 15 loaded is 9, okay, I mean immediately within the 15 and 9 together. So, then 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, okay. Again 15, right, and at that time again it will get loaded immediately, this 9 will get loaded. So, how many unique states are there? 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, okay, and 15 and 9 are together. So, you can see that the unique states are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, it is a mod 10 counter. Now, instead of 1, 0, 0, 1, you could have loaded any other thing, and in up count mode and down count mode, there could have been different modulo numbers available depending on your requirement. Okay. So, if you are instead of say 1, 0, 0, 1, if you are loading say 0, 1, 1, 0, okay. I mean this 0, 1, 1, 0, then what will happen? So, instead of 9, you are loading 6. Instead of 9, you are loading 6. So, from 15, it is coming over here. Okay. So, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 6 together. So, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So, mod 9 count will be there. And similarly, over here, it will go in this direction and again it will get loaded 15 and 6 together, it will give you mod 7. Okay, 7 unique states, right. So, this is the way with variable preset you can have different kind of such things. Now, to end this particular class, we shall have a look at one simple example of getting a digital clock using multiple counter and an arrangement to calibrate it, to set the time right. Okay. So, what you see over here is this is the 1 Hertz clock, okay, which you know how to design using a 555 timer, or if you have any other arrangement, some stable a stable multi-vibrator generator, that also you can use. Ultimately, what you need at the input is a 1 Hertz. So, every 1 second there is a trigger coming. Okay. So, this is going to the seconds, this is going to the seconds is feeding to the minutes and minutes is feeding to the hours. So, every 60 seconds, so it is a, you can have a mod 6 and mod 10 together, right, and another could be your what is it called, for minutes also a mod 60, and for hours you need a mod 12. Okay. So, this will be the unit decoding, that means 0 to 9, and then this is 0 to 5, the tens place. Okay. So, 59, then it will go to 0 0, 0 to 59, 0 0 to 59, then it will go to 0 0, and at that time when it reaches that 59 to 60, that means mod 60 counter, 1 clock trigger comes over here. Similarly, for count of 60, 1 clock trigger comes over here. So, this is the way the cascaded counter that we have discussed before, the same thing in a bigger framework. Okay. So, that is one part of the story. The other one is what you see, the switches that are there. So, to calibrate or to set the initial timing, right, you first disengage this one, the set seconds, right. Then what you can do, if your current time is say 350, okay. So, you can put this one, you just connect this one, press this one, depress this one. So, basically this will get connected. So, this now clock is feeding here. So, every 1 second there will be a change here in this hour count, okay, every 1 second, because now 1 Hertz clock is now feeding it directly. So, whenever it reaches 3, you stop there, right. So, after that you put it over here, I mean remove the depression. So, it will come back, it there is a spring load by which it is coming back, okay. It is through a appropriate switching mechanism, right. Then you go to minutes. So, if it is 50, again you wait, if its initial value was 30, then you have to wait for 20 seconds, 20 such things will be there, and it will be coming here, okay. And then you release it. So, it is set, the minute part is set, and then you engage it, then the counting starts, okay. Is it fine? So, this is the way we can have a digital clock in place, and it is how you initialize it, set the time correct. Okay. So, with this we conclude using asynchronous reset, counting state 0 can be enforced early and in a clock cycle in which a specific count is reached. Okay. So, 0 0 0 0 will be there whenever that particular number count value reaches. This helps in getting a modulo number of one's choice, but a glitch occurs because the state causing reset appears for a short duration. So, in the final class on this counter, the next class, we shall see that what could be alternate arrangement by which we can get this glitch removed, okay, or we can have a different kind of counter design paradigm. The internal two input AND gates are useful in counter ICs to effect asynchronous reset to obtain different modulo numbers, okay, that we have seen. IC 7490A provides a fixed asynchronous reset of 1001 along with a asynchronous reset to set the modulo numbers. 74193 we have got variable preset which offers a lot of flexibility, and also we have seen that a digital clock can be made using counters when we can have a mechanism to initialize it. Thank you.